Okay, so I'm going to make a pretty terrible video on how to work the first problem from the 366 problem set. I got a couple texts from people asking about the problem set and how to go about solving it. So first thing you're going to do is hop online, go to the NCBI website, go down to nucleotide, and put in the accession number that Dr. Hemmerling gave us. Now there's a newer version of this one, but I suggest just working with the number she gave you. There is a 0.2, but I would just use the 008920.1. Nope, that's wrong. Why didn't it work? I must have typed it in wrong. Good video so far, right? That's what we're looking for. Okay. So when you first get to the sequence, just go down till you see the first exon. Click on that. And what you can do is you can go through all the exons in it, all the useful information by going to this little bottom menu. The question asks for sequence 2. So what I typically do is I like to copy it and throw the sequence I'm going to be working with into a little folder, into a little file, sorry, so that I don't lose it as I go through the next ones. Then I like to go to pick your primers, put that sequence in there. You can put in different parameters for your primer, but I don't know that any are better than anything else, and this typically picks the best ones for you. So when you run this tool, it actually takes a minute to go through and pick primers for you. Now, one of the bad things I found with this is I think the primers that it picks pick a region outside of that sequence. So you'll see why saving it in another file comes in handy after. Oh, I think it loaded up back there. So it's just thinking really hard about how to get this sequence out. So you're really just trying to amplify this region of DNA. Ooh, that'd be bad, hold on. So I typically just Google primers design tips, and it's going to take you to Life Technologies. You can see it's a purple link. I've used it before designing my own primers. Here's a whole bunch of rules on things that make for better primers, because in the end I think that the primers that this thing chooses aren't great for getting the whole region. Yeah, see how they kind of pick inside the gene. If you want the whole gene, you have to design your own from the original sequence. So we'll go back here. So you have this sequence. What you want to do is have a length 18 to 30 nucleotide. You can figure out the melting temperature by using the formula she gave us in class, where it's 2 times A plus T or plus 4 times G plus C. You want your GC content. One thing it doesn't say here, but you typically want to end on a C or G. Oh, okay, here. Yeah, you want it to end on a C or G. So you just go back to this and look at the code. And so you're going to run this one backwards. So when you do your primer, it's actually C, C, T, T, G, C, T, etc., etc. You want to end on a C or G. And the forward one, I actually just used the first 20, and it worked out pretty well. Once you're done doing this, take whatever you designed for your primers from this sequence And again, I just started right at here and went 20 bases back, and from the top I went 20 bases forward. Just remember that this is the 5 to 3 direction, so your primer is invisible and underneath and is 5 to 3 reading backwards. So you can put those into another tool here. So let's take our primers. We want GTT, blah, blah, blah. And this will be our forward primer. I hate that it puts that little brown stuff on it. Now for the reverse one, just read up there. What is that? That's pretty good. That's 19 and 20. So what you want to do with these sequences now then is to run them to make sure that they have a similar melting temperature, because you're not going to want to run PCR on things that have wildly different melting temperatures. Ignore that. Ah, come on, computer. So go to pick your primers. Say that you want to use your own. So take the sequence that you've got over here and do it less sloppy than I am. In a lot of cases, I've ignored the brown stuff, and I think maybe when I deleted that, some of it disappeared. You're going to want to be more careful than I'm being. I'm just doing it quickly to show, so you can actually get primers for this. And it'll tell you even what the melting temperature for your primers that you've chose have been, and it'll tell you what affinities they have for other things in the human genome. So again, you just wind up waiting on this for a minute. And then once you're done this, what you can do is you have these pieces. I like to take the polymerase that blunts the ends and do a blunt-ended cloning exercise to get it in there. So here you can see that it okay, so it's within a couple degrees. Okay, it's actually 3.4. So if you wanted, you could add a couple more onto your reverse, and that would actually get it closer in melting temperature. The more bases you have, the more heat it takes to denature them. But I think this would be okay. Again, just be careful. You're going to probably want 20 bases forward, 20 bases backwards when you do it. Self-complementarity is not bad, as you can see here. GC content, decent. So these are decent primers. They'll get you out of it. So then you just do a blunt-ended cloning exercise. You can really cut Puck19 with whatever you want at this point. So you can cut it with any restriction enzyme. Then after I cut it, I like to take that restriction product and make it blunt-ended by adding, again, I think it's the T4 polymerase. It'll actually chew it back for you, so you wind up with blunt ends. Then you use SIP and SAP on your vector to stop it from re-annealing to itself, and then you add your blunt-ended little piece of human hemochromatosis, and it will then affix itself to the now SIPed or SAPed Puck19 clone. If you remember, SIP and SAP is that calf intestinal phosphatase or shrimp alkaline phosphatase, and what they do is they get rid of the free 3' OH, so you can't just re-anneal it to itself. It's called autoligation. You don't want that. So then you're going to put this in, you'll ligate it, etc., etc. Just run through that. That should be good enough to get you started. I didn't realize it was due tomorrow, so that's why I made this. So I'm just looking at the other questions really quick. They should be pretty straightforward. Yeah, it's just primers with obvious mistakes. Again, you can go to the Life Technologies website to find out what those mistakes are. The last one is Sanger sequencing. You read it from the bottom up. bottom up is 5 to 3 prime. And you can just write that on your little template there on the back page of the assignment. So it's 5 to 3 from bottom to top. Alright, man, that should help you out. That should get you done before you show up tomorrow. I didn't realize it was due in class. I thought we had more time. So take her easy. Take her easy, 366.